Okay, we were discussing the characteristics of different components of the traffic system. We discussed road users, okay, and which types of road users we discussed? We discussed characteristics of two types of road users, which were vehicles are road users, pedestrians and road users are human beings. Pedestrians and so the visual acuity and reaction process was for jinns. Drivers, yeah. Okay, drivers. Yeah. Okay, so we discussed two types of road users, but there are others. Okay, but drivers and pedestrians are more important than the others. Okay, and they obviously they are more in number as well on the roads. Then we started discussing the characteristics of vehicles. Okay, and we said there are how many types of vehicles? Four. You count it. And another one. Okay, recreational vehicles. Okay, and we said that the characteristics of vehicles which are important for us are again there are four, which are braking, the opposite of braking, acceleration, and low speed what? Turning, which we discussed, and support according to the size of the vehicle, and then there is high speed turning. So today we start with high speed turning. Okay, you can still see the slide, right? It's okay if I stand here. Okay. Because I have to. Yeah, at high speed turns, the radius of the curve has to balance the forces which are acting on the vehicle. Okay, so there are two design parameters which balance the forces which are acting on the vehicle at high speed. And high speed means more than 10 miles per hour, which is around 16-17 kilometers per hour. Okay, so any turn which is made or any curve which is designed for a speed of more than 16 should be satisfying the equation which you see on the slide. So in this equation, we are using E, which is superelevation. We are using F, which is friction. We call it side friction. Side friction, because this is for turning. This is different from another friction which you will see later on. So side friction, and then we have S. S for speed, yeah. Okay, and then we have R. Radius. Okay, so the two design parameters which we are trying to use are, which of these are design parameters? Which are the things, these two things we design? Radius and friction. We design friction. Superelevation. Superelevation. Okay. So these are the two parameters. But in the end, both sides of these equations, this equation should be balanced. And how did we drive the equation? There is a complete derivation in the highway engineering course. Okay. So in this equation, you can see there the term 0.01 E. So that is the value of E basically, because E superelevation is in percentage, right? So E is basically the cross slope. The cross slope of the road which you are providing at the curve. Okay, so that's some percentage, vertical upon horizontal, but across the section. Okay, and then we have another term which is E into F. So E is some fraction, some ratio, 0.0 something. And then f is again a fractional value in decimals, less than 1. So if you multiply two terms, both of them are fractional, then what will happen? The answer will be even smaller than both of them. Okay, so that term becomes almost 0, negligible. Okay, so in this equation, the first equation, E into F is considered negligible, and whatever the remaining equation was, we took R on the left hand side, everything as on the right hand side, and you know the parameters. Okay, what are the parameters? You already know. Okay, now in this equation, the first equation which you see, everything is in the same units, R and S and M, everything is in the same units. Okay, but we know that the speed of the car is not measured in feet per second or meter per second. Okay, it is either measured in kilometer per hour or miles per hour. Okay, but the radius cannot be in kilometers and miles. Radius smaller. Okay, so we need some conversion. Convert the speed from miles per hour to feet per second if you are using the feet system, or to convert the speed from kilometers per hour to meter per second if you are using the metric system. Okay, so now you see the other equations are with the conversion factors. Okay, conversion factors are included in them. Anything else? Yeah, the value of G is also included. G is what? What is it? The gravity. And it's not 9.8. 9.8 is in one unit system, which is the metric. The other one is 32.2. So whatever unit system you are using, it will you will put the value of G in that system. Okay. So this, in the second equation, the number 15 includes the conversion of speed from miles per hour to feet per second, and also includes the value of G, which is 32.2 in this case. And the last equation, 125, includes the conversion of speed from kilometer per hour to meter per second, and then it also includes the value of G, which is 9.8. Yeah. Now, one thing which we will use later on as well, you see both of these terms are in the denominator, right? 15 and 125, and the denominator. Now, usually, if I have to put a constant, it's easier to put it in the numerator, right? Above the division, it's easier to remember and so on. Why are we complicating the equation by putting in the denominator? Because if you do 1 upon 15, if I have to put it up, I have to take the inverse, right? So if you do 1 upon 15, or the other case, 1 upon 125, the answer will be very small. Okay, so we are putting in the denominator intentionally so that the number is significant. Okay, clear? Now we have the value of E and F. For these values, we have some ranges. Okay, some table from which we can take the value. So superelevation ranges from 4% to 12%. Yeah, normally from 4 to 12%. Okay, but if you feel, obviously it depends upon the speed of the car. So if you are designing the road for a higher speed, superelevation should be lower, higher, lower. Okay, let's vote. Who says higher? The speed is higher, superelevation is higher. Raise your hand. Okay. So the other people are saying superelevation should be lower, speed is higher, right? You didn't see I raised my hand as well. I was raising my hand. I was giving you the hint. When speed is higher, superelevation has to be higher. Okay? The superelevation is basically pushing the car towards the curve. Okay, so it's supporting the car to go along the curve. Okay, I think there is. Yeah, it's in the other chapter, I think. Anyways, there is a figure in the other chapter, we'll see it. Okay, but super elevation is basically you raise the outside edge of the road. Okay, so it's like this. Okay, and the car is on this surface. Okay, and it is going in this direction. Okay, the inside direction. Okay, the left hand side direction. Okay, so the slope is pushing the car towards the curve. So at high speed, the car needs more push to go towards the curve. Otherwise, what is the initial movement of the car? To go straight, right? So you are providing a super elevation, the car is pushed towards the curve. Okay. So when the car is at high speed, it needs more resistance. Okay, to go towards the curve. So the range is from they say 0.5% fine, from 0.5% up to 12%. Okay, and the trend is for higher speed, I should be providing higher super elevation. Okay, it will also keep in check your radius. If you are designing for high speed, still you can provide low super elevation. But that would mean in order to balance the previous equation, the radius will become very high. Okay, so that's why I said there are two design parameters: super elevation and radius, both. If you try to reduce one, the other one will automatically increase. Okay, so you have to balance both of them. Okay, so usually at any part of the road, 0% slope is not given. Cross slope is not 0% because of drainage purpose. Okay, 0% slope means water will not flow. Okay, which is dangerous. So even if the speed is very low, okay, and you can manage without super elevation, we still provide 0.5%. Make sure that the water is not accumulated. Okay, and then you can go up to 12%. I told you the reason. Yeah, if you have if you are designing for a region in which there is snowfall and too much rain, so the pavement is usually wet, or there is snow on the pavement, then there is a chance that too high super elevation may result in the car sliding. Okay, because obviously all the cars don't have new tires and so on. The pavement also gets old, so the friction decreases. Okay, what they call the grip of the tire increases. So to accommodate for these types of cars and to accommodate for the wet pavement, we avoid very high super elevation. Very high means 12% and 11%, and we try to avoid it. Okay, because at high elevation, super elevation, the car may be sliding. Okay, for F factor there is a table, very simple. This table is generated through experiments. Okay, so there is an experiment which is known as pendulum experiment. Okay, so you have a small part of the tire attached to a rod, and that rod goes over the surface. Okay, so you can so that part of the rod, the end of the rod has like a tire. Okay. So it goes from the pavement and it goes from the surface, and the friction is recorded. Okay, so they had the whole experiment for that. So they already did that, and they came up with these values for not the worst case, but very close to the worst case. You can see these factors are for wet pavement. Okay, but wet doesn't mean that it is totally underwater. Get my point? Okay, so there was water on the pavement is still wet, but there is no layer of water on the pavement. Okay, pavement is wet, but the water is not over the pavement. Get my point? Like you wash your hands, the hands are still wet, but this doesn't mean that the water you are carrying water. Huh? So this is a condition. Okay, so it's not the worst condition, but close to is lower than the normal condition. Okay, and again you can see the value of F does what when you increase the speed? the value of f decreases. Okay. Common sense, because if it increases, then you cannot attain the high speed. Okay, so this question is very easy. You are given with the speed of the vehicle. Okay, the maximum super elevation is given 6%. Okay, and the f value is given. Even if I don't give you the f value, you have this table. The speed is given, you can take f. F is given, you can take speed. Okay. In this case, they gave us 4, but the value is not the table. Okay, and you are required to calculate radius. You can do it, right? Okay. How much is the radius? Just for the sake of the class. How much is the radius? We have this equation, and we are using this equation with the constant 15, not the other one, because the units are in miles per hour and feet.
That's a big number.
What is the big number?
204.
Okay. Okay, so this is in feet, remember. It is 1/3 if you convert it to meters. Okay. And miles, then divide by 1,000. So. Okay. If I want to reduce this, what should I do? If I say I don't have that much space,
Reduce the speed.
increase the super elevation or reduce it. Yeah. Okay. Okay. This is slightly different. The radius is given. Okay, and super elevation is given, and then they are asking for what speed should be allowed on the highway, or what speed can be achieved on this curve safely. Okay, so you have the equation again. What should we do? So the problem here is you have S and F, both are unknown and both are dependent upon each other. If I could have got S from somewhere else or F from somewhere else, if I give you another equation for F, from here you can get the value of F, then you can calculate S. But here the problem is there is no other equation, there is only one equation, and that equation there are two unknowns, and both of them depend upon each other. Okay, so I cannot take one value and then calculate the other value separately. Okay, so as she said, what's your name? Okay, so here we have to assume a value of f. Okay, and that value of f is related to or linked with the value of s. Now, if the equation gives me the value of s, which is shown in the table, for that value of f, I am correct. Otherwise, I have to revise my assumption. Okay, so now usually it's an advice. Otherwise, you can assume any value of f because we don't know. Okay, so you can assume 0.32, you can assume 0.1, 0.15. It doesn't matter. Okay, but the advice is that you start from one of the ends. Okay, so that you know where to go. If you start from somewhere in the middle, for example, if I assume 0.15, if it doesn't satisfy, I don't know. Should I assume higher or lower? But if you assume, let's say 0.08, you know now only I can go back. Okay, so if you put 0.08, f as 0.08, how much speed you get? So you are putting f, but you're not putting speed. Okay, speed you are calculating from the equation, and you're getting
41.
41. Okay, According to the f value of 0.08, it should have been 80. Okay, so your assumption is not correct. Now you can go back. Okay, another advice, you can do one by one, no problem. Okay, so after 0.08, you can assume 0.09 and 0.1 and so on and so forth. Okay, but you can see the difference. It should have been 80 and you got 40. Okay, so there's a lot of difference between the assumed value and the value which you are getting from the equation. So I don't have to do it step by step. I can jump, for example, from 80 to 60. Okay, so if you put 0.12, f as 0.12, are you getting 60 or close to 60? You're getting 46. Okay, it's still not the assumed value, but you are getting closer. You see, it was 80 and 40, now it is 60 and 46. The difference is getting less. Okay, so let us assume 50 then. So if you assume 50 means I'm saying that you take the value of f as 0.14. 0.14. No? 48, 49, approximately 49. Yeah. So where was I? Yeah. Now the you can see that you assume one value 40, you got 40 or 41, then you got 46, and then you got 49. Okay, the next value in the table is 0.14, sorry, 0.15, which is for 45. Okay, now you already went from 41 to 49, right? So 45 cannot be the value. Okay, 45 cannot be the value. It can either be between 49 and 50. Okay, but we cannot do more because there are no other values, right? You can interpolate a value for 49 and try again. You may get the exact value, but that interpolation will not achieve anything because you see the difference of f values between 45 and 45 and 50. The difference is 0.01. So how much will be the difference between 49 and 50? 0.00 something. Okay, so there is no point of doing interpolation here. Okay, so we'll stop here. You can assume the value of speed as 49. Okay, and f is very close to 0.14. That's fine. Okay, whatever f you have exactly for 49, it will be 0.140 maybe something. So not a big deal. Okay, so the safest speed in this case is 49, and f is almost 0.1. Clear? Any questions? Okay. So we talked about low speed turn, high speed turn. Now we talk about deceleration and acceleration. Okay. So starting with braking or deceleration. So if I ask you for distance using the speed, you would do what? How do we calculate distance?
Time versus the speed.
Okay, give the distance, right? Now, if this is true if you are going at constant speed, but if you are braking, your speed is changing. Okay, so in order to calculate the braking distance, we don't use speed into time. We use average speed into time, average of initial value and the final value. Okay, which is what you see on the slide here. Braking distance equals to average speed into time. Average speed is the average of initial and final speed. Okay. Now, if you are stopping, then your final speed is 0. So the average of initial plus final will be
Initial.
only initial.
Only
Average.
Initial over 2.
Initial over 2. Huh? Initial plus 0 over 2, right?
Yes, sir.
So initial over 2. Okay. Now, the time depends upon your deceleration rate, right? The time depends upon deceleration rate. Okay. So how do you calculate time using deceleration? What is the relationship between time and deceleration and acceleration? What is it? The only difference is this sign. If you have to calculate time, and if I give you the value of acceleration or deceleration.
Acceleration.
Sorry?
Speed over acceleration.
Speed over acceleration, right? Acceleration is what? Speed upon time? Acceleration is what? Speed upon time. Okay, you don't remember? Yeah, it is. Okay, speed upon time. So time is speed upon acceleration. Okay, so we said average speed is initial plus 0 upon 2, which means initial upon 2, and then we said time is speed upon or deceleration in this case. Speed upon deceleration. So if you put both values, so s is the initial speed, so average of initial plus final is s upon 2, and t is s upon a. Okay, so if you multiply, you get s square upon 2a. Okay, so then you see they have further modified it, and now it is dB is 1.075 s square upon a. So what is this now? 1.075. A conversion, okay, to from to conversion for what? What are we converting here? What should we convert? No, but you're converting what, s or a or what? Is feet, right? Because the distance is supposed to be in feet, and acceleration or deceleration also measured in feet per square second. So they are already matching. You don't have to convert it. The only thing you need to convert is just feet. And for speed, we already used the conversion factor earlier. Okay, I'll show it to you in the same chapter. So we are converting the speed from miles per hour to feet per second, because everything is in feet and second. And then we are doing what? We also did what? Yeah. When I, ask you something, I'm not a intelligent person. Okay, that's why I'm teaching. So when I ask you something, the answer is not difficult. Okay, but your problem is you start looking at my face. Like you will see the answer here. You're not seeing here. Okay, so I am saying look at the moon. How round it is, and you are looking at my finger. No, it's not round. It's a straight line. Okay. So don't look at my face. It doesn't look like moon. Look at the slide. What else did we do? We converted the speed and where is the gravitation? Now you are inventing things. Well, I'm asking about 1.075. Okay, so if you convert miles per hour to feet per second, it's not 1.075. It's 1.47 actually. So why are we putting 1.075? Because we did what else? We converted speed and come on over to and what else? Yeah, something like this. So the s was squared, so the conversion factor has to be squared and then divided by 2. Okay, so 1.075 is the conversion factor squared divided by 2. Yeah. Okay. Then now there is a here. The deceleration depends upon two things. A is deceleration, right? Deceleration of the car depends upon two things. The gravitational force, which is basically a measure of weight of the car. We earlier discussed that if the vehicle is heavier, deceleration will be slower and acceleration will be slower and so on and so forth. Okay, so the measure of weight is basically the gravitational force. Okay, and the other thing is the friction. The friction between the tires and the pavement. Okay. So A depends upon friction and gravity, both. Okay. Which is why you see the equation here. F equals A upon G, or A equals F into G. Okay. F, which is the friction, the skid resistance, equals A upon G, or A equals F into G. Yeah. Now this F is not the F which you have used in the radius equation. Okay. That was side friction. This is, thankfully they are calling it a different name, is skid resistance, but it's also a friction, but it's along the path, along the pavement. That one was across. If your car is moving like this, if your car is moving north-south, side friction is east-west, across. Okay, the skid resistance is along the path. The car is moving north-south, this skid resistance is north-south. Okay, again that direction. Clear? So their values are different, their meaning is different, their direction is different. Okay, so you cannot put the value of one for the other. Okay, and they are used in different equations. Okay, so A will be replaced with F into G, and G is a constant, whatever unit system you are using. Okay, so here they are using feet for the time being. So they will put the value of 32.2. Okay, and then you get the equation which you see over there. Okay, after putting the value of 32.2, again, if you do 1.075 upon 32.2, it will be a very small number. So to avoid the small number, what did we do? We took the inverse and put it in the denominator. Okay, so instead of getting 0.00 something, now you have 30 in the denominator, which is good. Okay. Now in driving this equation for braking distance, we assume that the final speed will be 0. But in many cases, the driver doesn't want to stop. Okay, the driver doesn't want to stop, so he wants to get to another speed. Okay, so this equation will change for that. And another factor is, in this equation there is no effect of gradient, but gradient does have an effect on braking. If you are going upwards, the braking will be shorter, like the braking distance will be shorter, and vice versa. Okay, so this is the equation after putting the effects of or after considering the final speed as well as the effect of gradient. Okay, so the effect of gradient is basically added with the skid resistance and the speed initial minus 1. Okay, now here we are talking about braking. So initial is always initial is always higher than the other. Okay, so if you consider the other case that is not braking, then you have to change the sign of A as well. So the whole equation should become positive again. Got it? If you are talking about acceleration, then the whole equation will change. Okay, the numerator, denominator both will change. Got it? Okay, but we mainly consider braking. Okay, yeah. So in this equation we have a value of F. Okay, now we said F is A upon G, right? Now G is a constant. G is a constant. Okay. H2, we talked about H2 earlier. So H2 gives us the recommended value for A as well in both unit systems. They gave it in one unit system, then I found another book in which it was given in meter per square second. H2 doesn't give any value in feet. Okay, but some guy did it, and the value is 3.41. Okay, so how much will be F then? Give me the value of F. So F is A upon G. Give me in feet. Okay.
Zero point 347.
0.3478 and in meters. In bar. Yeah, you are changing units on both sides, right? It's a ratio. If you are using meter per square seconds here, then G is also meter per square second. It doesn't matter. 0.348. So F is 0.348, no matter which system you are using. Clear? But the assumption is the driver is decelerating at the recommended rate, what the ASTO found. Okay? So the value of F doesn't change because of the units, it may change because of the deceleration of the driver. Got it? What?
We are wanting to work on the link.
Okay, so this is the equation in meters then. Okay. Okay, so for example, there is this, some boulder, some rock, something on the road, and the driver. Okay, so the braking distance starts from here. Okay, I should move here. Okay, so the braking distance starts when he has pushed the brakes. Okay, and what did we call the time till he pushed the brake? Perception reaction time. Okay, so braking distance is not covered in perception reaction time, it is covered after that. Okay, so an accident happened. Vehicle hit the abutment of the bridge. Abutment means the side, the wall of the bridge. Okay, the wall or side of the bridge. Okay, and these car manufacturers and mechanical engineers, they have some sort of method to calculate the speed of the car based upon the damage, because when they make the car, they do these tests to test the strength of the car and strength of the parts. They do these tests, so they have some relationship. If the car damage is so much, how much would have been the speed? Okay, so an investigator calculated the speed based upon the damage, that the speed at which the car hit the abutment was 20 miles per hour. Okay, so the car hit the abutment at 20 miles per hour. Leading to the point where the car hit the bridge, he saw some skid marks on the road. What are skid marks? Yeah. So obviously the poor guy didn't want to hit the bridge, right? So he was trying very hard to stop the car. So when you hit the brakes very hard, okay, and suddenly at full, full power, then the tires are skidding on the road and they leave these black marks. Okay, so those are skid marks. So if you see the skid marks, that only happens when the driver was braking, right? So skid marks are indication that to this much distance the driver was braking. Okay, so if you can measure for how long the skid marks were, you know for how long he was braking. I mean in terms of distance. Okay, so they measured the skid marks. Okay, and obviously the side of the bridge. It's the side of the bridge. So you have the road, and then you have a shoulder, and then you have the abutment. Okay. Now in many cases, the surface of the shoulder is same as a pavement. Okay. But in this case, the shoulder was made up of grass. Okay. So the F value changed. For the pavement, the F value was 0.35. For the shoulder, the F value was 0.25. Okay. So they saw 100 feet skid marks on the pavement, and then they saw 75 feet skid marks on the shoulder. Okay, and there is no gradient. So what we need to calculate is the speed of the vehicle at the beginning of the skid marks. What was the speed of the driver when he pushed the brakes? Okay, so we know the speed at which he hit the abutment. Okay, now if the pavement surface was same, F value was same, then there was no problem. We have the equation. The final speed is given. You want the initial speed, and you have the distance. Okay, but the only problem here is I cannot calculate or I cannot apply the total distance because the F is different. So I have to apply the equation twice. One for the pavement, the other for the shoulder. So from where should I start? The pavement or the shoulder? Pavement? Shoulder, because we know the final speed for the shoulder. Final speed is for the shoulder because abutment was after the shoulder. Got it? Okay. So you have this. So the skid marks on the shoulder are 75 feet. So the braking distance on the shoulder is 75 feet. The final speed is 20 miles per hour. Okay. And the equation is this one. Okay. The one on the left hand side. So SI is to be found. SF is 20 and F is 0.25 for the shoulder. And dB is 75. How much is the speed here, initial speed?
Yeah.
31. Okay, then give me the initial. So now what do we do with the pavement?
This will be the final.
This will become the final. Okay, initial of the shoulder becomes the final for the pavement. At this speed, the vehicle left the pavement and entered the shoulder. So initial for shoulder, final for pavement. Okay, so now you need the. So this becomes final speed. Again, you need initial now. Okay, the braking distance is 100 feet, and F value is 0.35. No gradient, G is 0.
What was inside?
So the initial speed at which the driver started braking is this one. Okay, any questions? Clear? Okay. Okay, so the animation which I showed you, so there was a rock on the road, okay, and the driver is stopping. So we said that he will push the brake at some time, and after the brake, the distance is measured as braking distance. Before he pushed the brake, he saw the rock, okay, and then he would have taken some time to decide, this was unusual, so he would have thought, okay, what should I do? How fast I'm going? Should I stop? Should I move to the other lane and so on? And then he would have pushed the brake. Okay. So this time is what we said? Perception reaction time. Now, if you calculate the time from when he saw the rock till the time he stopped, that total time is known as total stopping distance. The total stopping distance involves or includes two things. Which are those? Perception reaction distance and the braking distance. Okay? And it is measured from when you detected, remember, the first stage, detected, saw the object till the time you stop completely. Okay, and this includes the time taken by you as well as the time taken by your vehicle. Clear? So now you see here, D is the total stopping distance, and you remember you can identify the second part of the equation, and the first part is what? Perception reaction distance. Okay, and what did I do? Distance equals
And the speed
speed into time, and 1.47 is the conversion factor. This is the conversion factor we have been using again and again. Miles per hour to feet per second. Okay, this is the conversion factor, and then you see the second equation, the last equation. Okay, if you want to calculate the distance in meters. The conversion factor is from kilometers per hour to meter per second. Clear? So here you can see the conversion factor. In the previous equations, you are using the conversion factor and then doing something else with it. Here, this is the actual conversion factor. Okay. And what is 0.348? The F factor, that's scale. Okay. So they are saying that the vehicle is decelerating at the rate recommended by Ashton. Okay, our driver is coming around a curve, his speed is, okay, let us just complete this because we already discussed the equation. So our driver is coming around a curve, speed is 65 miles per hour, level grade means no gradient. Okay. When something is level, means no gradient. Okay. Now you will ask me in the exam. Okay. So there is a science which is called as numerology, where they will take your name and convert it into numbers. You study that. Okay, because if I give you level and then you ask me what is the gradient, I will not tell you. Okay, so then you use numerology to convert L, E, V, E, L into a number. Okay, whatever number you get. Okay, and then I will give you an F. So he sees a truck at 350 feet. This driver sees a truck at 350 feet. And if the driver is able to decelerate at a rate of 10 feet per square seconds, at what speed will he hit the truck? Okay, so you see what did they do here? Huh? They already decided. Yes, you will have an accident. So that just so you know, you can do something. Okay, it will kill a person just to have a problem. Okay, so you have now, yeah. So you have this equation. Okay. So what are we trying to calculate? Final speed, SL. Okay, initial speed 65, and DS 350 feet. Okay, anything and yeah. So initial speed is 65. T is you remember I showed you a table with perception reaction times for different situations, right? Okay. So normally perception reaction time is taken 2.5 seconds. For normal conditions, 2.5 seconds. You can go back, you will see that 2.5 seconds. So T is normally 2.5 seconds unless it is mentioned otherwise. Okay, so T is 2.5 seconds, SI is 65, and you are calculating the final speed. Anything else should I change here?
No, there are some points.
Yeah, so 0.348 will not work. I have to calculate F on my own because the deceleration rate is given as 10. Okay, so first of all, give me the deceleration rate. Oh, sorry, the F value, which is 10 upon the gravity. How much? 0.31. Okay. So now initial is 65, T is 2.5. You are calculating the final speed. Don't use 0.348, use 0.31. So how much is it? And the distance is 350 feet. So how much is final speed? Somebody has got this value?
Yes.
Okay. Okay, 56.5 miles per hour going at 65 miles per hour. So, why did this accident happen? Because he
He was using his phone.
he was using his phone. How do you know?
But I was doing
Why did this accident happen? Because he think about
Did not apply
technical.
the brake.
Did not apply the brake
Exactly.
at the right time. Okay. Anything else?
the brakes were
Or not good? Because maybe the reason is, how do you know that? I can know that. Because of the
slippery grade. Oh, the cave is slippery grade. There is no grade.
so when you say the brakes were not good, how do I know that? I can know that.
The braking distance will.
Braking distance you calculate it. Something given here in the question. Before you calculated the speed, you calculated what did you calculate? F value. F value depends upon deceleration. His deceleration is lower than what the ISO is recommending or expecting. Okay, maybe the brakes were not good or he did not understand the situation. Okay, but the main thing was he did not see the truck with more distance. He only saw it when he had 350 feet left between him and the truck. If he had 500 feet or maybe 1000 feet, maybe he would have stopped before hitting the truck. Get my point? Okay, and this is what we will talk about on Sunday. Okay, the reason was that when he saw the truck, he only had 350 feet. Okay, so this is something we will talk about on Sunday. And the last point is, in the previous example, the accident example, we were only dealing with braking distance. Here, we calculated total distance. Why not braking distance here? Who told me you need to calculate braking distance? 350 feet is not braking distance, it is total stopping distance. Who told me that? Who said that this 350 feet is not braking distance, it is the total distance?
Because from the moment he saw.
The moment he saw. Okay, distance, when the distance is measured, when you see something, this is total distance. In the last example, it was the distance of the skid marks, not when you saw the abutment. Okay, so the skid marks obviously braking, that is another indication, but here the distance is given from the point when he saw the truck, so that is total. Clear? Any questions? Okay, thank you.